Log on, tune in, find out. Another good idea from Cambridge.
It will be Carola-Bibiane Schönlieb from here, no, from there, right?
Yeah.
From there, and she'll be speaking about alternating total variation in minimization for pet reconstruction.
All right, thank you. Okay. Okay. All right, perfect. Yeah, so first, thanks a lot for inviting me and for giving me the opportunity to... Yeah, sure, a long way. No, but what I'm going to talk about is like, started out as an experiment, and it is a very unconventional approach, I would say, to the problem we want to solve, which is positron emission tomography reconstruction. So I'm very happy, especially because of this, to talk about this here, just because I'm curious of your opinion about this. So this is joint work with two other people who are here, Thanasis Focas and his postdoc Paolo Emilio Barbano. And just because I believe in transferring the simple idea first before going into the details, I just would like to phrase in a few words what I want to tell you. So positron emission tomography, the measurements that you get, the data that you get from a positron emission tomograph, constitute the radon transform of the image that you want to reconstruct. Okay? So the measurements are the radon transform. So they live in projection space, and they're also called sinograms. Okay? The basic approach, usually when you think about variational approaches, so this is also what I'm the approach that I'm going to follow. The inverse problem of inverting the radon transform usually is done via a regularization technique that happens in image space. So you say you want to invert the radon transform to go to your image space, to the object that you want to reconstruct, but you are imposing some regularity on your image, which is, for example, the total variation. Okay? The approach that I'm going to follow is a little bit different, because the main regularization that we are doing is not on the image, it's not an image space, but it's in the projection space, it's on the sinogram. And what I would like to convey to you is the idea that it is worthwhile to look at the sinogram, and especially at the structure in the sinogram, and to preserve the structure. Okay, so this is the main approach, or the main idea. And I want to go to tell you about this by following these 4 points here. So first I'm going to tell you what positron emission tomography is. Then how you mathematically reconstruct the image from your positron emission tomography measurements. And then I talk about our approach, and I will show you some numerical examples. So that's the plan. All right. So what is positron emission tomography? It's a medical imaging tool that is used to study functional characteristics in inner organs of the human body, like the brain or the heart, and not even only the human body, also animals. And it is used, the use is quite spread already in medical practice. It's used in neurology, oncology, cardiology, and so on. And as I said, the basic mathematical problem to solve here is to invert the radon transform. Okay? But of course, this is also complicated because what you actually measure is not the whole radon transform, but that first of all, you just have a finite number of measurements. Okay, so your radon transform the measurements that you have are just samples of the true radon transform of the object that you want to image. And then you have other interferences like noise, of course. Okay. So how does it work? So as a patient, you go to the doctor and you get injected a radioactive tracer, which goes through your body, which walks through your body, let's say, and it concentrates in regions of organic tissue, which are of higher metabolism, which are higher activated. So it concentrates there, and then it is experiencing a radioactive decay, and by this radioactive decay, it is emitting a positron. Okay, so, and this positron is again wandering through your body until it meets an electron, and it is reacting with this electron. Positron and electron are annihilating each other, and this annihilation process will result into a pair of gamma beams which are sent out from the position where positron and electron meet. And this pair of gamma rays is what is measured by the PET tomograph. Okay? All right, so that's how it works. So to be more precise, the measurements that you get from your PET tomograph are line integrals of your image function, of your distribution inside the body, which are weighted by something that I'm not going into in much more detail, but these measurements are weighted by a factor which somehow takes care about the attenuation that the gamma rays are going through by wandering through the rest of the tissue until they reach the detector. Okay? All right. So, of course, as I said, usually the measurements are not the pure radon transform, but first of all are sampled versions, are samples of the radon transform, and then they're also noisy. And the noise, and this is also very interesting in PET, is not what imaging people most of the time are dealing with. Is not additive, but is multiplicative. It's Poisson distributed. And this you will also see how this actually will show in the different kind of approaches to reconstruct the image from these measurements. So you have these measurements. How do you reconstruct the image? And there are two main methodologies to do so. There are the so-called direct methods, which aim to approximate the radon inversion. For example, the filtered back projection algorithm. Okay, so you have your measurements, and you want to compute the image by inverting the radon transform, and you approximate this inversion process. So the main characteristic of these direct methods is that they usually don't have an intrinsic noise model in the, well, that they do not model intrinsically the noise distribution. And then there are iterative methods which aim to invert the radon transform under the condition that you know that your data, that your measurements have a certain distribution. Okay, so that's why they intrinsically model the noise distribution. And they usually do so in an iterative way, and a main keyword here are expectation maximization algorithms. All right, so our method is a kind of a combination of both, as it is inspired by a direct method, but it is iterative in nature. But before actually explaining you our approach, let me just give you an idea about these two classes of methodologies that we have in PET. So the first example is a direct method, is filtered back projection. And filtered back projection amounts to compute a filtered version of your image. So U is your image, and you compute a filtered version of this image by going through basically these three working steps. So what you do is you first of all compute the corresponding filter in projection space, in radon space, by saying that the filter in image space is nothing else than the back projection of the filter in the projection space, where this back projection operator is just the adjoint of the radon transform. And after computing this filter in radon space, in the projection space, you filter your sinogram, okay, you filter your measurements, and then just look at this, at the red part of this equation here. You take this filtered version of the radon transform and you back project it, and by these line of arguments that I'm not going to specify more, you get that this is actually equal to the filtered version of your image. Okay? So this is the main idea. You compute a filtered version of your image by filtering your sinogram and then back projecting it. And of course, the performance of the filtered back projection algorithms, there are a lot of versions of this out there, crucially depends on how you choose your filter here. Okay? So this is filtered back projection. An iterative method is, as I said, expectation maximization. So here you assume that your data G is Poisson distributed, and think about K as the radon transform. So as the radon transform of your image is the data. And you express this assumption of the Poisson distribution of your data by maximizing the a posteriori probability density that says that your data is Poisson distributed. Okay, so this is this distribution here. And you can amount to solve this maximization of this a posteriori probability by an iterative procedure, which is called expectation maximization algorithm. Okay. There are also regularized versions of this approach, which is, for example, the TVEM algorithm, where additionally of assuming that your data has a certain distribution, the Poisson distribution, you also impose a penalization that forces your image to have a certain regularity. What turned out to be a reasonable assumption for images is, as we have also heard in Projean's talk yesterday, that they have a small total variation. Okay, where this term here is the fidelity term for this Poisson distributed case. So it's basically just what we have seen before, just this maximization of this a posteriori probability, just phrased in a variational framework here as a minimization, not a maximization. Okay, so this is just the noise model. So this is the term for the noise model, and this is the term for the regularization. Just to have this in mind, our approach will somehow also be a variational approach like this, but rather than regularizing the function that you want to reconstruct, you regularize immediately your data. Okay. So why do we want to regularize your data, and why are we actually searching for structure in the projection space? So these are just a few examples of sinograms that you might encounter in PET imaging. So why are we searching for structure in those? Okay, so these are just some line integrals. And one motivation that we actually got to know only later on in our project is a work by Jean-Philippe Thirion, who is doing the following. So he proposes an algorithm, an edge detection algorithm for PET images, by not detecting the edges in the image, but by detecting the edges in the sinogram. Okay. So what is the intuition for this? Well, if you just look at this graphic example here, you see, so this is your object, okay? So you have one disk and a smaller disk inside. If you look at the corresponding sinogram just of the boundaries of these two disks, you will get two lines in the sinogram for this. And the basic assumption now in trying to detect edges rather in the sinogram than in the image space is that actually edges in the sinogram correspond to object boundaries in image space. Okay, let me give you another example from Thirionn's paper on the next slide here, where you see if you follow, for example, this line here in the sinogram, you will have a corresponding line if you apply the inverse Radon transform. Your corresponding line in the image will be along the boundary of this object here. Okay. Okay, so this is, so to say, to give you an idea why we are searching for structure in the sinogram. Okay. So what do we want to do? We want to do the following. We want to solve the pad reconstruction problem by minimizing this functional here. So you compute from your noisy sinogram, you compute a denoised sinogram by minimizing, say, a balanced version of two regularization procedures. So you want to balance regularization on the sinogram, which we model by total variation minimization. You want to balance this against a regularization in image space. And here I just took as a first approach, just we don't want to regularize much, okay? We just want to, say, have a sparse solution in image space. Okay, you can change this, but for the moment, I just phrase it like this because we really want to see what happens when our main regularization happens on the, in the projection space. Okay, so these are the two regularization terms, and then we have a fidelity term, which at the moment is just the L2 norm between the noisy sinogram and the denoised sinogram. So this model is well posed, so you can prove existence and uniqueness of minimizers. And before showing you some pictures, let me just again emphasize on the three terms that we have in this sinogram here. Let me talk a little bit about those. So first of all, the TV regularization of the sinogram. So I motivated this a little bit already with this algorithm of Thirion. But another motivation is that before you want to invert the Radon transform, you somehow maybe want to enhance your sinogram in a way that decreases the spatial and angular sampling error. And by regularizing your sinogram by a differential regularization, you make a connection of your discrete points both in the spatial and angular direction. Okay, so you have some kind of smoothing of the sinogram already before inverting the Radon transform. And then, as I said before, and this is also again motivated by Thirion, additional to this differential regularization, we want something that is not linear but nonlinear, because we want to preserve some structure in the sinogram. So this is the idea. So that's why TV versus H1, we actually prefer TV. So what happens if we do this? And here, just show you a toy example, which was constructed by a pad simulation code of Frank Wibbeling, so thanks to him for providing us with this. So just starting with the toy example, just to see what this TV regularization is really doing, okay, in the projection space. So this is your noisy sinogram. This is the corresponding object by just taking the sinogram and computing the filtered back projection result. And then you see, when you go from left to right, you see the regularized sinogram and the corresponding regularized image with an increasing weight on the total variation regularization term. Okay, so you increase your TV regularization when you go from left to right. And you see in this example in the middle, you see exactly what I said before, and this again connects to Thirion, because when you apply TV regularization on the sinogram, you're enhancing all the edges in your sinogram like this, and you see this actually also in the object space. So you get these kind of radial lines here, okay? Which is of course not what you want. So you regularize more to just preserve the say the most characteristic edges in your sinogram. You regularize more, you get this kind of result, and you regularize even more, and you get this. So this is now, so just to keep in mind, so we have just constructed this with actually basically only regularizing the sinogram, because what we do in image space is just shrinkage, okay? It's just assuming that my image is sparse. But here, we apply the main regularization, and that's what you get when you take this and you compute the filtered back projection of this. So this is what you get in image space. Okay, so you see that your edges here are actually very well defined, also in object space. By enhancing your edges in the sinogram, you're actually enhancing your edges in the object space. So again, so why do we only do L1 regularization in image space? Well, the first motivation, as I said, was just to see the kind of pure TV minimization effects that my TV minimization on the sinogram has in image space. Another motivation is that what you actually know about the radon transform, about the regularity of the radon transform, is that the radon transform is more regular than the image. So you could also argue that we actually want to do something more regular on the sinogram and something less regular on the reconstructed image. Nevertheless, we can also try, if we change this procedure now to having TV here in the sinogram and TV in the image, what do we get? Well, we get something very similar. Actually, on the projector, it looks even more similar, but so you get something very similar. So I can tell you the difference that I see here on the screen is that still, when you only regularize with TV on the sinogram, you can still see these kind of, you know, they are fading away when you kind of increase the weight on the total variation regularization, but you can still see these kind of radial lines in the image. When you do TV on both, you will just see a flat disk here, and you see the nice boundary here. Okay. Just to compare it again with what does TV regularization on the sinogram actually give to us. So this is again the object, just computed via filtered back projection. This is TV regularization only on the sinogram. This is the result with TV regularization on the sinogram and on the image. And this is when you just take the result of the filtered back projection and put it into and compute the denoised version of this via total variation minimization, via the Rudinow and Fatemi model. So what do you see here? I mean, in the center of the disk, all of these kind of examples look more or less similar. But you see that actually the edges, if you really put the effort into enhancing the edges both in image and projection space, you see that the edges are much nicer resolved when you actually do this kind of double regularization procedure. Okay. Yeah. So what about our fidelity term? So first, when I started, I kind of told you that it's important to model the noise distribution. So now what we're doing here, we just have a fidelity term which is additive. Well, this is just the first coarse approximation of the truth, okay? You could, for example, easily change this coarse approximation to something that is better adapted to the noise model, but still staying with an L2 fidelity, but with varying regularization parameter, and this regularization parameter is chosen depending on the statistics of your image. So there are various methods out there at the moment which can do this. Or you can, and I think this is the best approach, actually you can go to replace this quadratic fidelity term by the fidelity term that we have seen in the TVEM algorithm, okay, which really models the Poisson distribution. So this we haven't done yet. This is still to come. We just stayed with a simpler version for the moment, okay. So how do we solve this? And the basic idea for the solution is the following. So you have this functional here. So you have your noisy sinogram. And then you compute the regularized sinogram by minimizing TV of G, okay, with a regularization parameter alpha plus beta times the inverse Radon transform of G in L1 plus, and then we have the fidelity term here, G minus G tilde squared. All right, so to simplify our life, what we do first is we introduce a new variable which we call U, and we set U equal to the inverse Radon transform of the sinogram. So U is my image, okay? I don't know if you can see it, but so U is my image, and then instead of solving a minimization problem for the sinogram only, we solve now a joint minimization problem for the sinogram and for the image, where we minimize now over U and G with the constraint that U is equal to the inverse Radon transform of G. And we get the following. So we get alpha TV of G plus beta times the L1 norm of U plus lambda over 2 G minus G tilde squared. And again, this is still complicated to solve because we jointly have to solve this minimization problem for G and U. So what we do is we first transform this constraint minimization problem into an unconstrained minimization problem by replacing the constraint that U should be equal to the inverse Radon transform of G by a Bregman procedure, okay? So by an iterative approach, so we have an additional variable B that we have to update in every step of our iteration. So this, instead of having this constraint exactly, you just have to go here with your iterations to infinity to impose the constraint correctly. Okay, so that's the main idea. So you replace this constraint minimization problem by an iterative unconstrained minimization problem. And then you split your joint minimization of U and G into two minimization problems, where you alternatingly solve a minimization problem for the image and for the sinogram. Okay. So this again, so this procedure, which is called split Bregman algorithm, it was proposed by Goldstein and Osher in 2009. Is actually nice because it also mimics our main regularization idea, which is that we both want to regularize in image and sinogram space, and we do this now alternatingly. Okay, so this is why the title of the talk is called Alternating PET Reconstruction. We can also show that this split Bregman procedure is actually converging to a solution of our original minimization problem. So this is just done by a couple of putting together a couple of results from papers from convex analysis, where where the basic thing to show here is that the split Bregman procedure is equivalent to a Douglas-Redford splitting, for which you have convergence results. And then, so the nice thing now about the splitting is that each of these minimization problems is now straightforward to solve. Okay, so the first problem for the minimization in image space is just a shrinkage problem. So it's an L1 minimization problem which you can solve directly via shrinkage. And the second minimization problem is a total variation minimization problem, which we solve by a combination of approximating the original TV minimization problem by a sequence of surrogate functionals, and then we apply Chambaud's algorithm. So I'm not going into much more detail about this, just to say that the TV minimization problem, the sub-minimization problem here, is solved by an iterative procedure, which is very standard. And you can even choose something else again. You could even again apply some kind of split Bregman methodology to solve this here. It's just it's just that this is what we chose, let's say. You can speed this up probably by doing something else, but this is what we have. Okay. So I've shown you numerical results up to now just for this toy example of this very of the large disk, which is a dominant object in your image space. You can also, just to emphasize that we can not only reconstruct very large scale features, but also small scale features. You see here on the left a noisy sinogram. Again, this is simulated data, so you have a noisy sinogram of two disks, and if you regularize, and here we have just applied the TV L1 regularization procedure, so just regularizing in the projection space, you get this kind of result for the sinogram and for the object. But of course, we are not, the simulated data is not the real world. So let me show you some examples for real measurements. And here, we kind of made a compromise between two things. So we wanted real measurements, but we still wanted to validate our approach by having some kind of ground truth. So what we did is we took real data for the so-called Chesek phantom, where the first row of examples I show you are measurements for the coarse section of this phantom, for this. And the second example that I show you also includes a finer section of this Chesek phantom. But first, just the coarse section. And for this, I don't want to confuse you more, but the only real data that we got was not PET but SPECT. It was just easier for me to explain to you what PET is. It doesn't change a lot in the algorithm. Okay, it just changes how you actually invert the Radon transform if you have SPECT rather than PET data. So for you, everything stays the same. Just the Radon inversion is a little bit different because you have your attenuation coefficient that you had at the beginning this exponential in front of the Radon transform is now actually depending on where you are on the line. And the SPECT data is constructed by not a pair of gamma rays, but it's only sending out one ray which is measured. So nevertheless, so we apply this here. It doesn't change a lot for you, as I said. And we apply this TV L1 regularization procedure. And here on the left, you always see just a filtered back projection of the noisy sinogram, and on the right, you see the TV L1 reconstruction. So this is I show you now examples for going from low noise level to higher noise level, where what I mean with this is that this data was constructed by taking several independent copies of the same object. Okay, so the phantom was measured several times independently, and low noise level means that we took more information, that we took more of these samples together. And the higher noise level gets, the less of these samples we took. So that's the main idea. Okay, so that's the filtered back projection results. This is the TV-L1 reconstruction. With higher noise level, you see this. And with even higher noise level, you see this. Okay? So it's not perfect, but it's just that we wanted to see how do we actually resolve the small holes in this Jacek phantom. If we go now if we stay at this higher noise level, but we go to the finer section, where the filtered back projection result looks like this, I want to show you now another combination of what we do with not filtered back projection, but a more accurate way of inverting the radon transform. So what I show you is that the same algorithm that we had before, but instead of inverting the radon transform with the filtered back projection, we do this via an algorithm which is due to Fokas, Iserles, and Marianakis from 2006, where they propose a numerical computation of the analytic formula of the inverse radon transform. Okay, and what you see when you go to the next slide, and this is just a zoom in. So this is the fine section, and this is the coarse section. And you see, even now comparing the coarse section, the regularized version of the coarse section, with the regularized version with the same noise level, but with just the filtered back projection inversion, you already see that it also additionally pays off combining this TV regularization technique with a very accurate way of inverting the radon transform. I'm not going to talk about this, but I think Paolo is going to talk about this on Thursday a little bit more. The key point is that a combination of accurately inverting the radon transform and regularizing in the right way, paying more for regularizing both in image and measurement space, you can actually get very, very nice results. So yeah, just to compare this again with the phantom. So this is the result. This is the phantom. Of course, for the fine section, we also couldn't we couldn't resolve all the fine scale features. But you have to see that this data was very, very, very noisy. So all right. So to conclude, what I've shown to you is maybe a very unconventional approach to PET reconstruction, where we aim to reconstruct our image by an alternating regularization procedure in measurement and image space. I've shown you TV regularization, but you could go to higher order TV, for example, because one disadvantage of TV is the staircasing effect, so you get these kind of piecewise constant images, which is maybe not the right thing for the sinogram. So we chose TV because we wanted something structure preserving, but maybe we want something structure preserving which is still smooth enough. So so this is an extension which one might want to think about. Then I've shown you two kind of results. The one where you just compute your inverse radon transform with a filtered back projection, and the other one with the analytic radon inversion, where you see another improvement, another step of improvement if you put more effort into this. And the to-dos, actually, which I didn't list all here, but the to-dos are, of course, now if only, I didn't compare our method with any other reasonable method, okay? So since our method is an iterative procedure, it would be worthwhile to actually compare it, for example, with EMTV or things like this. So this is still what we have to do. The kind of, let's say, theoretical, interesting thing to think about is what does it actually mean if we regularize with TV in radon space? Okay, can we somehow characterize solutions? Can we characterize solutions when we regularize in radon space? What does it mean in image space? Can we somehow quantify this? So this is something that we still have to work on. So yeah, so I think this leaves me to thank you for your attention.
Questions, please.
Yes, I was just wondering if you can, maybe it's connected with the last point you put on the last slide, but when you have this variational framework and you have terms in terms of the data and the solution, normally the data is associated with the likelihood, which is easy to understand if you're using Kullback-Leibler or something like this.
Yeah, yeah.
When you add this constraint of TV, what's the interpretation in the Bayesian sense of that?
In the sense of the statistics of the of the distribution. So as I said, so one thing that we still have to do is actually to replace this very coarse approximation of our Poisson distribution. At the moment, we don't take care of this.
But the TV is an extra term, which
TV
means
is an
it's like an
extra term,
extra modification of the statistics. Of the
Yes, yes. What you know about TV is that you get these piecewise constant minimizers. What it does to the noise distribution, this is also with EMTV, for example. So you regularize an image space, but you're still changing the distribution of your data, right? Still, you're trying to keep this with this Kullback-Leibler term, but you're still changing your data in a certain way. I'm not sure if, well, I don't know actually if you can say something about the statistics that you get with TV regularization. Yeah, I mean, you try to balance this all the time with the right modeling of the fidelity term. Yeah. Mm-hmm.
Actually, two questions. So the first one, when you're regularizing over the data space, you started with noise which is, let's say, not correlated. But when you finish regularizing, you end up with correlated noise.
Yeah.
That's maybe the first question. The second question is, the radiant transform in principle is smoother because you're looking at an integral, correct?
Right.
So the
yeah,
functional
that's what I said.
space, the functional space that the data belongs to doesn't seem to be supposed to be
Smooth enough.
TV. Well, actually, it's maybe too smooth. I mean, do you want to really use TV for that?
Well, okay. So the motivation to use TV was to have something that is structure preserving. I agree that this is maybe not regular enough because you really get these kind of stairs in your sinogram, which you see actually in the image, which is not nice. Okay. So you want to go maybe to something more regular, but I'm still convinced that you want to preserve the structure in the sinogram. So you want to balance this. So that's, for example, why I said maybe you want to go to higher order TV or something like that. So I agree that you want something regular in the radon space. Okay, that's why we also at first modeled this TV regularization versus just L1 regularization for the image. But I still think that you want something structure preserving. Yeah. Well, just of the kind of intuition that you get from looking at the correspondence of structures in the sinogram and the image.
Probably we need to start the next lecture. Can you please discuss it after the next lecture? Thank you very much.
Yeah, thank you.